So, hello everybody and welcome to session number 15 of my lecture on statistical energy analysis and hybrid methods. In this session, we come to the core and the heart of statistical energy analysis because we talk about diffuse wave fields, which are a perfect model to describe random subsystems. Good. So, why are we doing this? When we accept the concept that a complex system can be described by simple quantities like energy intensity or other basic static quantities, we have to relate those quantities to wave quantities like pressure or velocity of a plate or the pressure of a cavity. Those quantities we call engineering units in the SEA context. If you would like to do so, we need a model for a reverberant field. And one excellent candidate for such a model is a diffuse wave field that is represented by random plane waves. So we just assume that we have several plane waves with arbitrary direction and random phase and amplitude. When we deal with such models, we have to consider that for each dimension we have different statistics of those models, and all the statistical quantities, for instance the cross-spectral density, will have different results of the in the reverberant field. So just denoting that we have three-dimensional system that we deal with, two-dimensional or one-dimensional. Good. So now let's come to the details of this model. So as mentioned, we assume plane waves, and they have arbitrary direction given by a vector wave number k, given here in the figure by all the k with index I. We have an amplitude, a random amplitude, and phase. And this is all summed up to a total wave field, which is given by an arbitrary wave quantity denoted here by the figure psi. And this sums up all the wave of the different wave numbers given by k. It could also be by scalar using direction vector, normal vector n. So this consists of the random amplitude given by psi index I and the head for the amplitude. Random waves with a uniform probability in a wave range of an angle range of 0 to 2 pi. This is why the probability is just the reciprocal of 2 pi. In the plane wave model, if we have all directions with the same value, it's obvious that there's net zero power flow in the field. So if we just take an area here, there's no power flowing into different directions. Also important for such plane wave models, important to deal with the boundaries, and at the field surface we have a different situation. We don't have the full angle available, obviously, because there's a hard wall or something different, and the waves are reflected. Why do we need it? The point is that we need such areas to define the loading at the surfaces or the boundaries, because this is where diffuse sound fields are exchange energy to the neighboring SEA or statistical field. Okay, so as mentioned, we have to deal with different wave numbers from different direction, and for doing so we use a uniform angle distribution, just given by a normal vector with a specific directivity, and this is described for the azimuthal angle here denoted by phi, and the polar angle denoted by theta. The combination of both are called the solid angles, and when we just would like to describe one specific polar normal vector, they are defined by those different components in x, y, and z direction given by the angles of the spherical coordinate system. When we talk about the three-dimensional space, we need the sphere, And if we are, when we're talking about two-dimensional space, we just need the circle for one specific polar angle, obviously. Okay, so for the derivation of the statistics, we just have to recapitulate some of the mean properties. So the mean value of the amplitude is just the mean value of all the single amplitude in our wave field. And the mean square value is just the average of the square of all amplitude values, or it could also call it the square of the root mean square, obviously. Good. When we think about the mean value at one specific position in our wave field, it's obvious that if we just consider the uniform probability and our given function for the wave field, for each single wave field, and if we then do the same and come back to and get rid of our complex notation and really use the cosine function, which is necessary here, we will end up with 0. And that's clear. So this is once again denoting that if we do the average of one position in space, I'm not talking about this because this is just the mean value of the amplitudes, it will be 0. That's a very important point. But this is not the case for the mean square value, but here we have another option, because then we get the squared cosine, and that the mean square value is the half of the squared amplitude, which is also an obvious thing, because this is what we know from other notations. Okay, so now let's discuss how we deal with the probability functions over all the angles. For the 3D case, we have the full spherical angle system with our polar and azimuthal angle running from 0 to pi or 0 to 2 pi. And the probability for one specific direction is given by this expression here. So it's a full polar space given by 1 divided by 4 pi. And the sine function denotes the different weighting depending on the polar angle, because there's more area available here at the equator of the sphere and less here on top. And the sine expression compensates that. In the 2D case, that's quite simple. We just have the polar angle of half pi, and then we're just circling around here in the plane. And for this, we have the same angle for the azimuthal angle, and the different probability function is just 1 divided by 2 pi. In the 1D case, we just have two discrete directions. Maybe sound a bit strange that this could be create a random wave field. But the probability, that's quite simple. It's just 1/2 for both directions, because we just have only two options. If we are interested in formulating this by an angle, we would have just two angle positions. Okay, good. So now let's derive some other statistical quantities, especially the cross correlation. For the cross correlation, we have to relate the shape or the wave shape at different positions, and we start with the location at 0 which is okay, for it's just our choice, and this would be the wave field at position x1 and for space and time, denoted by this mean value expression. We have to do the same for a second location, which is just described by a distance delta expression, so delta x, and a different time, which is just the time plus a different time delta. And then we have this expression for the second wave field average over all the different plane waves. So when we formulate the cross correlation of both, the only thing is that we have to use the conjugate version for the second. We got this double sum expression, which can be further simplified. So it's the expected value of this double sum. This can be simplified because by definition, so this is what was our choice, there is no correlation between different indices. So we get rid of the double sum, just ending up with a single sum, and using all those expressions that are related to a unique index. And if we do so, we can simplify the formulation here more and more, finally ending up with this expression. So this is the squared sum, and this is the version if we formulate this and using a continuous probability function. So summing up of all direction with the given probability, and including the time delta, the distance delta, and the normal vector which follows from this. However, this expression here is now the point where we have to select and consider all the different dimensions, and this is why we have to solve this separately for each dimensionality, 3 dimension, 1 or 2 dimension. Good. Again, in this model, we consider a common or an arbitrary wave field amplitude, and we have to relate this to the energy density. And for doing this in a kind of common way, we define a constant B that relates our wave amplitude to the energy density. Just to give you an example, if we say we're talking about pressure waves, this constant B would be 1 divided by rho c square. So this is what we learned from the energy density. If we talk about a plate wave field and so on, the B would be a different constant. From the energy density, the intensity follows directly, and that's quite a simple one because we have solved this. The relationship between energy and intensity is given by the direction of the wave and the group wave speed. And using the above formula simply gives the following relationship between the amplitude and the intensity. Okay, so now we go through all dimensions step by step. Again, as mentioned, for the one-dimensional diffuse wave field, we have a positive and negative propagation direction for one-dimensional systems. And we have, so that means that our expression k multiplied by delta, the delta and r is the distance of the delta of the distance of the microphone or whatever positions, is just plus minus k delta x. So we start with the intensity. So at one boundary, it's obvious that there's only one direction where the irradiation could come from. It's a one-dimensional system, making it simple. So that means we just have to sum up one option, and this would give us this expression here. So the intensity is the root mean square expression in our wave field by group speed, the constant b, and half. So what does it mean? That means the intensity is half the intensity of the free field with a similar RMS amplitude. Okay, now let's consider the cross correlation. So the cross correlation in a free field is just if it's, let's say, independent from the location, it's just given by the delta expression. So the delta in space, distance in space, and the delta t for the distance in time. And if we enter in the given formula before, just got switched back, and you know what I'm talking about, we just enter the simple 1D expression, and it's a discrete value of 1/2 and 2 directions. It's a sum that we are using here. And coming back to this sum again, we see that we have just to evaluate 2 options, this sum from 1 to 2, all the different directions, and then we just using a different expression here for this. We're using some trigonometric considerations of the details, and then we get the final result, which is given by here. That means the cross correlation is a cosine function k delta x and a cosine function omega delta t, which is quite a regular value of what we are looking for. Okay, so now let's come to the two-dimensional version of this diffuse wave field. In this case, we have propagating waves on our two-dimensional subsystem, and we use a plane angle integration. So let's start with the intensity again. So for the boundary condition here, we don't have the full angle. We're just using half of it, and we just introduce the probability, and we enter the probability of our two-dimensional systems, which is just 1 divided by 2 pi. So this is the expression for this. And when we solve the integral, we get the expression as given here. So that's the group velocity by our wave relationship constant divided by pi, and the root mean square value of our amplitude in the wave field. So again, just remember, in the two-dimensional case it was 2, and now we have, instead of 2, we have pi for the two-dimensional field. So this is why I said that we have to deal with all the things for each dimension separately, because we got different cross correlations in all different dimensions, and we got different relationship between the root mean square value here in the field, which and the relationship of this root mean square value in the field to the intensity or at the boundary. Okay, so far for the intensity. Now let's go have a look at the cross correlation. In the cross correlation formulation, we just select, we choose one direction without loss of generality, and then we can formulate this Ki delta R formulation by using a sign expression, which is the azimuthal angle that's given in the two-dimensional surface. Again, we use a probability function, in this case the 2D probability function, and apply the cosine expression as we have done that before. And just modifying this and going step by step through the math and extract all those parts that are not related to the integration, we finally got this expression for the cross correlation. Just remember, the cosine functions in the time domain, that's the same, but here it's a Bessel function. That's because the Bessel function is so this integral here is a formulation of the Bessel function. So instead of in the 1D case, it was also cosine, but here it's a Bessel function. So again, similar to the intensity, we have a different cross correlation for a different dimension. Okay, so now let's come to the last case, three-dimensional systems. You might expect that again we have another relationship for intensity and cross correlation in this context. So now we choose the normal vector in z direction, so to consider the orientation of the boundary plane. That means that our angular integration runs from the azimuthal. We use the full azimuthal angle range, but we just need only from 0 to 2 pi for the so this is the area here, 0 to 2 pi for the polar angle. So the normal intensity is just given by the polar angle, but it's independent from the azimuthal angle phi. So again, we're doing the intensity stuff calculation. So it's given by this expression. Now we have to integrate over two angles. We use the probability of the three-dimensional system, and again our expression for the wave field intensity. And when we enter the probability, so these are those components here, and we perform the integral over the half space, then we get the final intensity and root mean square relationship. And again, this is a different value. So it was a factor of half in the one-dimensional case. This was 1 divided by p in the two-dimensional case. And now we have 1/4. So this is a relationship between the intensity and the root mean square value of the wave amplitude quantity. Everything linked with our constant b, as denoted in the beginnings. Good. So last but not least, we now have to think about what is the cross correlation in the three-dimensional wave field. Similar to two-dimensional, we select one specific direction without any loss of generality, and this is the z direction, and that means that our distance vector k multiplied by the distance vector delta kr can be expressed by this. So it's k multiplied by r cosine the azimuthal angle. So this by choice of z we can use we can neglect the azimuthal angle and just using the polar one. Good. We do this to find the cross correlation and the probability again, enter the wave expression with using all the different formulations for k delta r and omega delta t. Then we use the probability function, as you can see here, that's hidden in those expression. And once we have solved this integral, we are ending up with this expression. So again, the time correlation is the same, but our Bessel function is now replaced by a sine, or we call it a sync function. So it's a sine of an argument divided by the same argument. Good. So again, so the global form of the cross correlation is kept for the half space locations, but two locations end of the walls at the 3D diffuse have the above correlation function. So this is quite practical because we can later use this in the verification of diffuse field reciprocity. This is quite well known in room acoustics. In many parts of literature, this expression is derived. The 2D and 1D versions are less popular. You won't find that in typical acoustic textbooks. Okay, let me summarize all those things. So I call it topology conclusion. So the relationship between the energy density and the normal surface intensities is described by a specific proportionality factor. This is beta d, and this and the relationship here that you will see in the figure, the different cross correlation, and you have a different cross correlation for the different dimensions, and this is shown here. So the 1D case, that was the cosine function, 2D, that was the Bessel function, and in 3D case, it was the sync function. So just decreasing more or less like the others. So this is given here in the summarized here in the table: cosine, Bessel function, sync function, and the relationship between energy density and intensity is also summarized here. So this is related for this beta d. That means it's 1/2, one-dimensional, 1 divided by p, and 1 divided by 4 for the three-dimensional space. It's worth mentioning that this is not all basic theory. If you would, for instance, make a test with 2 microphones in a reverberant chamber and get the correlation results, which is done here from a paper given by literature number 15, you see that this could also be measured. So this is not basic theory, it's really proven in a typical reverberation chamber where you have a practically related diffuse sound field. Okay, so once we have derived the relationship between the plane wave model, we understood the correlation and the energy intensity relationship, and now the next step is to see how can we deal with damping. And in the reverberant field, there are 2 possibilities for damping. So one comes with just the wave propagation. So there is a complex wave number which gives the damping in the wave propagation itself. And the other option is every diffuse sound field has to be contained in something, and that means there will be reflection at surfaces, and all realistic surfaces have some kind of absorption. So this is the second source for for dissipation in the reverberant field. How is this formulated? Again, we have this the power loss, which is given by the loss factor as it was defined for the oscillator and so on. That means omega multiplied by the damping loss factor times energy. This is our definition of the damping loss factor and gives the dissipation in the field. And the power that is dissipated due to boundary reflection, that's quite easy. This is the intensity multiplied by the area, the absorption area. And this is very important because here our constant beta comes into play, which is depending on the dimension. So that means, again, what is the absorption area? This is a so-called total absorption area, which is just summing up all the different areas surrounding a system with a specific absorption factor. And this is the average around it. And AP, that's the perimeter or the total surface area of our boundary. Good. And we sum all this up. We have a kind of global damping loss factor. So this is the dissipation, and which is coming from if we just formulate this in a version that might be related to a total damping loss factor, we can just have to sum up this. So we just take the dissipation value here, which is a simple one, but we add the above formulation of this, and then we get this expression, and in the parentheses you see that this would be the total loss factor of a random subsystem diffuse wave field, which consists of the wave contribution and the boundary contribution. And the boundary contribution depends on the dimension of our subsystem, or I'd say the surrounding boundary of our diffuse wave field. Means when we have an energy, we will have an energy decay, which is given by this. So starting at time 0, and then we will have an exponential function that decays by eta omega t, where eta is the damping loss factor. Good. Okay. So now let's come to another option. It's something that is quite often misunderstood because the relation of a wave quantity at the boundary. So just we start with the so-called autocorrelation, where we say that the distance is 0, and that is more or less averaging one position measuring in our wave field. And this is obviously the half of it, so the root mean square value, but we still have the time correlation. So just imagine that we have the situation somewhere in the field. We are summing everything up, and this gives us the average of all the of our, let's say, wave field, which is the root square of the root mean square. But, and this is a tricky thing, when we do the same at the boundary, we just always have only the half space available. This is the average of at the boundary, which is just half of the square of all our wave fields. So it's 1/2, but it's a 1/2 of the square, and that has some certain impact compared to a typical reflection. So the mean square value of the amplitude is half of the amplitude compared to the full angle in the field. Good. So now let's consider a different situation. When we have a reflection of anything, of a typical wave at the wall, we use a reflection vector, and the wave quantity that we have exactly at the boundary is given by 1 plus this reflection vector plus the incoming wave. If we say we have a hard wall, which can be assumed quite often, the pressure, for instance, is doubled, or the stress is doubled. So, and if we just calculate this, we just use the pressure factor, which is doubled then. But again, we have to consider this half effect due to the fact that we only have the half space available. That means that at the diffuse, let's say at the boundary, we just have the doubled squared root mean square, or the mean square pressure. In other words, the double amplitude that you normally have due to the reflection at the wall, it's partly compensated by the fact that only the half space is available. So that means when we have in a diffuse sound field, we measure a root mean square somewhere in the middle of our room or in the middle of our plate. It will be the square root of 2 of the other way around. So the boundary will have just multiplied by a factor of 2 of the root mean square amplitude in the field. Or in other words, if you have just one, we have just one plane wave hitting at the wall, hard wall, it will double. But in the diffuse sound field, it's just multiplied by the square root of 2. So that means it in a diffuse sound field, the pressure at the boundary is 3 dB higher. In a coherent wave that is reflected, the pressure at the boundary is 6 dB higher. Very important to note. But again, this is only a value that is valid for random subsystems. And this is very often used if you use excitation of SEA subsystems. So this is why I'm insisting so much on that. Good. Okay, again saying the factor of square root of 2 instead of 2 is just valid for reverberant field, and it very often leads to confusion. Good. So that's it for the model of the diffuse wave field using plane waves. In my next, I hope you enjoyed it. In my next session, I will talk about Monte Carlo studies on random systems. So we come back to the system idea of some of the earlier sessions, and we just will modify the parameters a little bit and create the average. And that means we try to create a random field or random subsystem by numerical studies, proving many of the assumptions that I've shown you now before in the model for diffuse sound field. So have fun with this session and see you later then for session number 16, dealing with exactly the Monte Carlo studies.